Okay, today we're going to talk about noble gas and ion configuration. We're taking electron configuration a little bit further with this. Just a simpler way to write it. Oop. Okay, we're going to start on page 2 of your notes, so just flip your page there. The Bohr model is a useful 2D representation of an element. A more useful modified Bohr model is easier to use. So the modified Bohr model is what we're going to talk about here in a second. The Bohr model is important because it shows the number of electrons per energy level. Each one of those circles is an energy level, remember that. It does not show sublevels, but it can help identify valence electrons. Okay, so a term you might be familiar with that we're going to talk about today, very important in chemistry. So this modified Bohr model shows the number of electrons per energy level. It does not show sublevels, but it is much easier to read and draw. So here we have, I'm going to use black. So we have lines like this that are going to represent the orbits or the orbitals, okay? Or the energy levels. Let's call them energy levels, okay? 1, 2, 3, 4, 5, 6 of them. And in a neutral atom, we're going to have 57 electrons, right? So that first energy level only gets 2, right? 1s. 1s2. Okay, so 2 electrons there. We're going to have 8 electrons here. We're going to go maximum of 18 in our third energy level, 18 in our fourth energy level, 9 here, and 2 here. So if we convert this to electron configuration for lanthanum, so this is lanthanum, this is what we would get down here. Now that is a real pain to write out. So we're going to work on a way today where we make that a lot simpler. So here we have lanthanum again down here at the bottom. What we're going to do is we're going to use the noble gas configuration. So here are our noble gases. They are noble because they are stable. They don't react, okay? The reason they don't react is because they have filled sublevels, okay? And that makes sense, though, because we're in the P block here, and we know that P gets 6, a maximum of 6, and to get there, we got 1, 2, 3, 4, 5, 6 right here. So every one of these elements has a filled sublevel, even helium, which is not a P block element. Okay, so we're going to use noble gases to kind of write a configuration that's a little bit shorter. All right, I'm going to erase that just for, okay. So looking at lanthanum right here, how we're going to do this, let's move to the next one. How we're going to do this is we are going to go up one level and over to find the most previous noble gas. And in this case, it's xenon. Okay, we got xenon right here. After xenon, we fill in the rest. Okay, so xenon's going to be 1, 2, 3, 4, 5. Okay, 5s. 4D right here. That's 4D. Remember the drop down. 5p6. Okay, so we can find that right here in the full-length lanthanum electron configuration there. Okay, that means that if we write xenon just like that in the brackets, we're representing all of this. And then we just fill in the rest. So xenon noble gas configuration will be written xenon in brackets 6s2 5d1. And here we have how it's represented. That okay, this noble gas represents xenon's electron configuration. And then from there we go to, this is a 5th principal energy level, our sub level, and the first electron. And again, to find the core element. The core element is the element in brackets, the noble gas. Go up 1 energy level and over to the noble gas. Using the periodic table, we're going to write the noble gas configuration for germanium, sodium, and cadmium. So go ahead and pause and try to do that by yourself. Okay, so let's identify germanium. It's right here. Okay, so to write the noble gas configuration, we have to go up and over and locate the most previous noble gas. And this is going to be argon, and then we'll go four S2. Three D10. And then the second electron in the one, two, three, fourth energy level. So 4p2. Okay. Go ahead and pause and do the next one. So let's go ahead and find sodium. Sodium is right here. Okay. The most previous would be neon. So we go ahead and just write neon. And 3, right? 3 S1. All right. I'm going to fill in these for you. Okay. Now cadmium. Go ahead and pause. Do cadmium. Let's find cadmium. All right. And the most previous will be krypton. So then we're going to go after krypton, we go to 5s2. And then all the way to, is it 4 or 5? It's 4. 4d10. Remember that drop down. We go from 5s to 4d. We go from 6s to 5d. Okay? All right, I want you guys to go ahead and do these on your own. Let's talk about periodic patterns. Okay, so there's obviously some patterns you've probably already noticed. So the period number, periods are the rows. This is a period, this is a period, this is a period, 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 period. So the periods are equal to n. They're also equal to the energy level. Okay, so we have our 1, 2, 3, 4, 5, 6, 7 periods and 7 energy levels. And if you number these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 18. You'll notice that these columns within the sublevel blocks equal the number of electrons in that sublevel. So, for example, beryllium has 2 electrons in the S sublevel. Let's talk about valence electrons. Valence electrons are the electrons in the outermost energy level. They are the electrons we're primarily concerned about in chemistry because they're the electrons that take place in chemical reactions. So just know that only the S and the P electrons are valence electrons. That's because they are the ones that are going to be further away from the nucleus. Remember, the D drops down. So let's go ahead and count how many. Well, first of all, let's identify this element. So we've got noble gas configuration here. Argon. But on top of that, after that, we got, before we begin, I'm going to label this. Okay, so after argon, we got 4s2. Okay, so going to here, 3d6. 1, 2, 3, 4, 5, 6. Okay, so identify the element. It is iron. And iron's going to have 2 valence electrons. Okay, because we are only counting the outermost electrons, the 4th energy level, in the S sublevel. We're not counting the D because remember, it drops down. It fills the inner energy level for 3 before, okay? Before it comes out and fills up the 4p, okay? So 2 valence electrons. Let's do krypton. I'm gonna erase this. Okay, krypton. Krypton is right here. It is our noble gas. And then on top of that, we've got 5s2, 4d10, 5p2. Okay, so we have 10. And we're going to have how many valence electrons? Well, we've got the p and the s, so that's 4. 4 valence electrons. Okay, let's do it again for xenon. Or whatever this element is that starts with xenon. So we start with xenon, our noble gas, and then we go to 6s2. 4f14. Remember, the drop down for these inner transition metals, the lanthanides and the actinides, is 2, right? So the 6 period drops down to 4f, okay? So let's go ahead and plot that. 4f14, going all the way through here. Here. Okay. Then we go 5d10. There. And 6p5. 1, 2, 3, 4, 5. Okay. So we're going to have astatine. And it's going to have the 6 energy level. It's going to have 7 valence electrons. All right. The octet rule tells us that atoms tend to gain, lose, or share electrons until they have 8 valence electrons. In this way, atoms fill the valence, the outer energy levels, which gives the atom stability of the noble gases. Okay, so that's how ions occur. Okay, ions are trying to get over here. I'm sorry, atoms are trying to get over here. So the losing or the gaining of electrons allows them to become noble, to have 8 valence electrons in their outer energy level, in their outer shell, if you will. So isoelectric means 2 atoms with the same number of electrons. Iso means same, electronic, electron. So same number of electrons. Atoms gain or lose electrons to become more stable. This is referred to as isoelectric with a noble gas. Okay, so let's look at these 2 examples here. We've got phosphorus, and we've got phosphorus with a -3 charge. Okay, you can look at let's find phosphorus first of all. It's right here. Okay, and the noble gas that they're using is neon. So neon is the 3s2, and then 3p3 for phosphorus. Okay, but if phosphorus has a -3 charge, that means it has 3 more electrons, which takes us all the way to the noble gas configuration equal to argon. Okay? And now we have 8 valence electrons. So phosphorus, by gaining 3 electrons, became more stable and now has a noble gas configuration of argon. This is why you find phosphorus in this state, in this -3 ion state, more commonly, because atoms want to become stable. That's their nature. And they do that by gaining and losing electrons. All right, so some exceptions for stability. Some elements will borrow from the S to compete a half or full sublevel. So if you just look at this periodic table there, the ones outlined in red have a full sublevel, right? So beryllium, for example, is going to be 2s2, right? So it's happy. It's got that full S sublevel. Okay, so it doesn't have 8, but it's much more stable than lithium, for example, which is a highly reactive element. Okay, and so sometimes they're happy with just getting to that full sublevel. Here, our half sublevels are these ones. Okay, these elements can either gain or lose electrons to become more stable, the blue ones. And just a couple of, you might want to outline in dark black, copper, and chromium. Copper and chromium are some exceptions. You would expect it to fill that S level first, but actually it's going to be more stable if it fills that D sublevel first, okay, with 1 valence electron. Same thing for chromium. Instead of filling up that S first, it puts 1 in the D, okay? So 1 of those electrons goes in the D sublevel. All right, so in 1944, American scientist Glenn Seaborg suggested that the actinide series should be placed below, like we have it down here, the periodic table along with the lanthanide series. Our modern periodic table took form. So this is what it used to be, okay? So I know it's kind of weird looking at it like this down here, like trying to understand where it goes, but I think this image kind of shows that a little bit, that these elements, if we're talking about energy levels, that's where they belong. Okay, so this is kind of a good visualization of that. Okay, so writing electron configuration for F block elements. We're going to go through D1 first. D1 is right here. Okay, but I guess to get to the F block elements, we are only concerned with those two. Okay, notice that these F block fit right in here, so right after lanthanum and actinium. Okay, so let's go ahead and write the configuration for gadolinium. Right here it is, 64. So what is our most previous noble gas? Well, we got to imagine that this row is right in here, right? As this row is going to be right here. Okay? So, going up and over, it's going to be xenon. Okay? After xenon, we have 6s2. Okay? After that, remember we're going to go through the D1 first. So, we're going to go 5D1 because we dropped down. Next, we're going to go to, you got to imagine now that we're here, we're going to go into the F, and we're going to go to gadolinium. Okay, so it's going to be 1, 2, 3, 4, 5, 6, 7 electrons. Okay, and we drop down twice. When I say we drop down twice, what I'm saying is that we started right here, right after xenon, came down to 6. Go through here, drop down to the D orbital, or the D sublevel, 5D1, drop down to 4F7, okay? So having these indicators here telling you that when we start the F, it's 4F, and then 5F, these little indicators are going to help you guys. Okay, so I'm going to erase all this because it's getting kind of messy. All right, so let's go with uranium. Uranium, we're going to find that right here, okay? And that's going to be 5F, all right? We've got to imagine uranium fits in right here. It's going to come right after that. So that means that our previous noble gas is radon. Let's start with radon. After radon, we go 7s2. Then we go 6d1. 6 because we dropped down. So even though we're in the 7th over here, the D drops down. So 7, 6D1, and then finish up the F with 5F3. All right, for D block elements, we're going to list the F block electrons, then D block. Okay, for D block, so we're working in here. For D block, list the F block electrons, then the D block. All right, osmium. Let's go ahead and find osmium. 76. Okay, what's our most previous? It's going to be xenon. Okay, let's start with writing xenon. All right, what's after xenon? It's (6s2). Okay, so now we're going to drop down and list the F block, then the D block, okay? Because that's going to fill first. So we're going all the way to osmium. So we're going all the way from here to here. That means if you just imagine that this row here is right there, we have to go through it, okay? So it's going to take all of them, which is 14. So we're going to go 4F14. And then we're going to go 1, 2, 3, 4, 5, 6.